continuous transformation. Now, I'm not going to go into too much detail as to what these things are. There's a whole branch of study called linear analysis that details these things in a lot more detail than what we're going to consider. But we're going to be interested here in the idea of a continuous transformation. What do I mean by continuous transformation? Well, I'll tell you what a discrete transformation is. That's something that cannot be built up of little pieces. For instance, the rotation of a square, the symmetry of a square, are discrete steps. You cannot say that the square is symmetric under small little rotations. It's not. It's only symmetric under rotations by multiples of pi by 4. So, a square is an example of a discrete symmetry or a discrete transformation. Remember, I'm going to speak of the two interchangeably because the idea of doing something is transforming my space. So, on the other hand, a circle has continuous symmetries because no matter how small my rotation, the circle will be symmetric under those tiny rotations. So let's use rotation as an example. In order to discover exactly what I mean by continuous symmetry and continuous transformations, let's use rotation to understand this. So let's consider what happens when I rotate the point x, y in the plane by some infinitesimally small angle epsilon. So, to begin with, I can write x as r cos theta and y as r sine theta. Now, when I rotate through by epsilon, this is obviously where theta is this angle here. When I rotate this whole system through by epsilon, I get a transformed system. X prime equals r cos theta plus epsilon, and y prime equals r sine theta plus epsilon. Now I can write these out further. I can use the compound angle formulas to write this as r cos theta cos epsilon minus r sine cos sine theta sine theta sine epsilon, and this one I can write as r cos theta sine epsilon plus r sine theta cos epsilon. But epsilon is really small. And when epsilon is really small, it's going to make sense. And just how much sense it's going to make is astounding, actually, because it can cover everything. But it's going to make sense to do the Taylor approximations here of cos epsilon, sine epsilon, because epsilon is very small. So expanding these around 0, we get x prime is equal to r cos theta. Now, cos epsilon looks something like 1 minus a half epsilon squared right? And sine epsilon looks like epsilon minus epsilon cubed over 6, something like that. Now if I just write this to first order in epsilon, I get the answer of r cos theta minus epsilon r sine theta. That's order epsilon squared. This is the first order approximation. Now, we are conditioned to think that first order approximations are not in any way enough, that they're just an approximation. What's interesting about continuous groups is that it turns out that this is completely enough, given that epsilon is small, to determine everything else. That's something I want to drill in from the start. That the first order approximation can be used to generate everything back. Right. I'm not going to actually show that. I will ask it to everyone on Tuesdays or test. Really get down questions that you actually think about. Y prime. Oh, by the way, what's this equal to? What's r cos theta? What's r sin theta? Okay. So this one is r sine theta, and now I'm not going to bother with the whole tail extension. I'm just going to take the first order part, and I'm timesing, r cos theta, r cos theta sine epsilon, just looks like epsilon, plus r sine theta cos epsilon just looks like 1. So this is x, epsilon x plus y, or y plus epsilon x. So infinitesimally, a rotation operation looks like x going to x minus epsilon y, and y going to y plus epsilon x. If you look at it here, this motion here, which looks like x has gone backwards, minus epsilon y, and y has gone forwards, upwards, epsilon x. And you can see that it's true in certain limiting cases, like down at the bottom here, where only y moves upwards, tangent goes up. And that's obviously because the y value is 0 there, so we don't add anything to x, we only add y, and so on and so forth. But we've shown it in general, and certainly the special cases are of interest to us, that to first order, a rotation operation looks like this. And we call this an infinitesimal rotation. X goes to x minus epsilon y goes to y plus epsilon x. We call it an infinitesimal rotation. And in every sense of the word, it generates the entire rotation. What do I mean by generates the entire rotation? I mean, in the limit of epsilon goes to 0, and in the limit as you're applying many of these operations, right, you'll get a rotation. Proper finite rotation. So what you can do is you can, for instance, say, okay, n times apply the operation x minus theta over n, y, and y plus theta over n x. And if you apply this operation n times, right, where theta is any angle you like, and now you let n tend to infinity, what you'll get back is precisely these equations. Right. Try it as an exercise. So what it means is two things. One, we're doing an infinitely small rotation. Two, we have enough information encoded in that infinitely small rotation to do any rotation. And three, we're interested in objects that are symmetric under these infinitely small rotations. So not like a cube, more like a circle, where we can rotate infinitely small and it'll still come back to a circle. And as we do that, even if the rotations become finite, we still have a symmetry. Stuff like differential equations are often symmetric under infinitesimal transformations. In fact, they're much more useful than these finite transformations, these group theoretic type equations. And these are what you call Lie groups. Now, there are other operations like translation. Translation is really easy, right? Let's, for instance, consider x translation. I'm translating in the x direction. What's an infinitesimal x translation look like? Well, it looks like x goes to x plus epsilon, and y goes to y. And I don't think it takes any great degree of genius to realize that as I add up these little infinitesimal transformations, I'm going to get something that shifts me down. Right, so x shifts and y doesn't. If I add these up, if I set epsilon to k over n, and then n tends to infinity, you can very quickly show that this just becomes x to x plus k and y to y. Right, so it fully generates any x translation. And we can do a similar thing with y translations. Now that we know what these continuous transformations look like, I'm going to define them in general, and then I'm going to prove a theorem, making use of the fact that mechanics is a variational problem. In other words, making use of the fundamental principle that we just showed, Hamilton's principle of least action. I'm going to prove a theorem by Noether that will enable us to use these symmetries if mechanics has these symmetries. If our problem has these symmetries, to come up with conserved quantities. Now what's interesting is, I think that in general, the universe, everything in the universe, and in fact, it's pretty easy to see this. If I shifted everything, this whole room, all of us, and this chair, a meter to the right, and I shifted the rest of the universe a meter to the right as well, it's not going to make any difference, right? If everything in the universe were shifted to the right, or everything in the universe were shifted to the left, there'd be no difference. And if you wrote down the Lagrangian for everything in the universe, you'd expect it to be invariant under changes, transformations like this. Translations. And in fact, it would be. Now, if I took everything in the universe and rotated it by a certain angle, likewise, we don't expect any difference. Because whether this is north or whether that's north and everything has been rotated in the entire universe, it shouldn't make a difference. So the Lagrangian for the universe should also be invariant under these rotation symmetries, these transformations that we derive here. So these invariances are fundamental. We expect whatever conserved quantities pop out from assuming these invariances should in general be things that we know about, conserved quantities that we've heard about. And indeed they are. So let's analyze the notion of Noether's theorem. I'm going to draw a picture to begin with. Let's say this is all my coordinates q's, it's a manifold contains my q1 and qn. And let's say this axis is time. So this axis really is one-dimensional. This axis you can think of as a many-dimensional thing. As I move in time, I also move my position, my orientation changes. As I move this chair through time, its orientation and position are changing. And they trace out a path in the Q space as time goes by. And we know something about this path. If the path starts at A and ends at B, we know that the integral from A to B of the Lagrangian over that path, Q, I dot, where these Q's are parameterizing this path, dt. We know this is the action, and we know that any variation in that action is 0 in that particular case. Now we're going to apply a transformation to it. The transformation is going to be a general infinitesimal transformation of the form qi goes to qi plus epsilon times fi of q1 to qn. Right? So this is none other than exactly the kind of thing that we've got up there. For the rotations, we had x goes to x minus epsilon y. So the first fi or fx was minus y. And we had y going to y plus epsilon x. So the second fi or fy was x. X. And for the translation in x-axis, where x goes to x plus epsilon times 1, so the f1 in this case was 1, and y goes to y plus naught. So epsilon times naught. So F2 would be naught in this case. Right, so in general, our transformation looks like this, let's say, right? And we can say that this is like taking whatever our Q path was and adding some small variation to it. Adding some small variation. We can call delta Qi, my small variation is simply Fi. And we've done something very similar to this when we were deriving Hamilton's principle of least action. Then we had a very specific thing. It looked like a variation like this. It was always 0 at the endpoints. Now it's not necessarily 0 at the endpoints anymore. We're just adding some variation. And that variation may or may not be 0 at the endpoints. So let's can that. And let's draw in what we've got here. We're adding to each Qi something at each time, right? So we're changing them. At each time, we're adding some offset. At each fixed value of time on the x-axis, we're adding some offset on the y-axis to the Q. And we get some new path. Right. Now, when we work out the action, I claim that my system, firstly, before I start out, is invariant under this transformation. That this is a symmetry. What does it mean for this transformation to be a symmetry? It means I do this transformation to the system, and afterwards, it's exactly the same as it was before. Well, if I do something to the system and afterwards when I'm following this new path, it's exactly the same. What's exactly the same? The Lagrangian is exactly the same. The integral of the Lagrangian, the action, is exactly the same. So if I work out, and now I need to be very, 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 very cautious in how I write this down. If I work out the variation in the action in going from this path to this path, there's been no change. Red lights here, because I will ask this in the exam as a kind of trick question. This is not 0 because of the principle of stationary action. This is 0 because we have a symmetry. This is 0 because when I go from this path to this path, the action is not changed. When I made my transformation over here, the system, the motion, the action did not change. So the variation in moving from this path to this path is 0. Yes.
All the points in the path have been transformed.
Everything has been transformed in the path, but after doing that, the action integral, the value of the action integral is exactly the same. And that's because it's symmetry. Yes. Okay, so this is just a translation into x. So I'm just adding epsilon to x. And epsilon is the same as epsilon times 1. And all I'm saying is epsilon times fi. So x here is 1. That's all. Right. So this variation is going to be 0. Now, the principle of stationary action does tell us something. It tells us that if we have a change in the path that is 0 at the endpoints, then the variation is 0. And we're going to be able to use that. But let's work out this variation. So 0 is equal to the variation in A when we go from this path to that path is equal to, now let's do it. We're integrating from here to here the action. So we're integrating, the time hasn't changed, the time still starts at the same value, and still ends at the same value. TA, TB. Doesn't change, right? Doesn't matter that we've shifted vertically, we haven't shifted horizontally. So the variation in the action looks like the integral from TA to TB, from TA to TB, and now we just write down the variation. We use our normal chain rule type thing. And of course there's a sum over I. But I'm actually going to take the sum over I out. It's implicit, it's assumed, right? So you know it's there, but it's actually distracting and getting you. But then you can know that it is there. Del O by del Qi delta Qi plus del O by del Qi dot delta Qi dot. Well, that's nothing we haven't seen before. That's just a chain rule for variations. That's what we saw in the review. That's what we saw on Monday and Wednesday. This is not special. Before somebody gets another point. Right. But now what happens is, this one is dotted. This one is dotted. So it's back to chain rule. We differentiate with respect to Qi and multiply delta Qi. Then we differentiate with respect to Qi dot, multiply delta Qi dot. How did we deal with this when we were deriving the principle of these actions? When we were deriving the Lagrange equations from the variational hypothesis? What did we do here? Integration by parts, exactly. The integration by parts. So we differentiated this one and we integrated this one. And we had a term at the endpoints. And that term was 0 because the variation at the endpoints used to be 0. But it's not 0 anymore. So that's all that we have to remember. And then we do this exactly the same way as we did before. We integrate from TA to TB. And we'll have in here del O by del Qi minus B by dt del O del Qi dot delta Qi plus the thing at the endpoints. And the thing at the endpoints, remember there's an implicit sum the whole time. There's a sum over I in front, I'm not writing. But the thing at the endpoints looks like del O by del Qi dot delta Qi, and this time it's not dotted, from TA to TB. Right, so what have we learned? Well, we've got a 0 on this side because this was 0 by symmetry. We have not yet used the theorem of least action, or indeed Lagrange's equations, which we can now make use of. The thing inside the integral upstairs, what does it look like? Lagrange's equations. What do we know the answer to that to be? 0. So indeed, we can replace that with a 0. And that's 0 by the principle of least action. You can say, well, indeed, just by mechanics. So we've currently got 0 is equal to delta A is equal to the integral from TA to TB of 0 dt plus, and remember there's a sum over I. Del O by del Qi dot delta Qi between A and B. Right, so this one is 0, this one is 0, so it must mean that this thing is 0. But this thing we can write out. What's delta Qi look like? Delta Qi is Fi. So we can write out sum over I, which I haven't been writing so far, but I'll put it back now, del O by del Qi dot Fi evaluated between A and B must be 0. Now, when I say evaluated between A and B must be 0, what does it mean? It means when I evaluate it at B and I subtract what it was evaluated at A, I must get 0. But if I can evaluate this at one point in time and subtract it evaluate it at any other point in time and get 0, what does it tell you about this point? It's the same everywhere. It's constant. i.e., this is called the motor charge, the sum of the I of del L by del 2I dot times by Fi. And I'll say conserved quantity. Now I'm going to use this theorem to derive some conserved quantities, and you will notice when we do this that they are very familiar indeed. But you will now have a new understanding of where these kinds of things can come from. So let's look at a particle in free space. For a particle. For a particle moving around in free space, it's got coordinates x and y, and the generalized coordinates. Like kinetic energy is a half m x plus 2 plus y plus 2. The potential energy, if we assume that there's a gravitational field here, is energy y. That's a two-dimensional problem. I don't think I'm adding another dimension or add no extra pizzazz to the problem. Right, so in the Lagrangian looks like a half m x dot squared plus y dot squared minus mg1. I claim that this has x translation invariance. Well, let's replace x with x plus epsilon. What happens to the Lagrangian? Nothing, right? Because when I derivative x, it goes away. So the Lagrangian remains invariant under x translation. That kind of makes sense. If I drop it from here, or if I drop it from here, we expect it to do the same thing. Fall in the same way. So this thing here is invariant. It has this symmetry. So let's find out what that means. Well, we have to do this. Some I dot O by the QI dot times Fi. Well, what is Fi? We have x going to x plus epsilon and y going to y. F1 is 1 and F2 is 0. Right? Or Fx is 1 and Fy is 0, if you like. So the motor charge is going to look like sum over I. Well, sum over I is just sum over x and y. So just take that away. This is going to look like del L by del x dot times by Fx. Plus del L by del y dot times by Fy. And that is del L by del x dot is just mx dot times by 1 plus del L by del y dot times 0, so it's 0. So the conserved quantity is mx dot. So what is mx dot? That's the momentum in the x direction. And it's conserved. So we're saying that translation invariance implies momentum is conserved.